The year is 2007. Inside Google's New York office, a build system freezes mid-compile. Engineers stare at their screens. 10 minutes pass, then 20, then 45. Somewhere, millions of users are searching, emailing, mapping their world, while the code that powers it refuses to move. If you've ever written software, you know that feeling. The spinning cursor, the bloated tool chain, the quiet dread of touching a single header file because you know it will trigger chaos. But beneath the clean, minimalist surface of a language called Go lies something deeper than syntax, a rebellion. By 2007, Google was processing more than 20 petabytes of data per day. Thousands of engineers worked inside a monolithic C++ codebase, stretching into billions of lines. Every delayed build drained productivity, an estimated $1 to $2 million per day in engineering time, closer to $3 million in today's money. Slow builds meant slow decisions. Slow decisions meant vulnerability. This isn't just the story of a programming language. It's a story about control versus chaos, simplicity versus power, human cognition straining against machine scale. The flight you book, the payment you send, the video you're watching right now, each depends on invisible infrastructure that must compile, deploy, and scale without hesitation. From Bell Labs legends to Silicon Valley giants, from quiet side project to global backbone of the cloud, this is the story of a language that wasn't meant to win. Golang wasn't created to dominate. It was created to survive. And survival changes everything. Chapter 1. When C++ became the bottleneck. Google didn't start with a problem. It started with success. By the mid-2000s, the company had grown into a distributed systems giant. Search, Gmail, Maps, ads. Each product ran on massive clusters of commodity machines, stitched together with intricate C++ services. C++ had power. It had performance. It had decades of battle-tested credibility. But it also had weight. As Google scaled past 10,000 engineers, something subtle began to crack. Builds that once took seconds now took tens of minutes. A single change in a shared header could ripple through thousands of files. Engineers would submit a patch, wait for compilation, then context switch to something else. Focus fragmented. Productivity bled out in invisible drips. The machine was powerful, but the humans operating it were slowing down. Internally, frustration grew. Not because C++ was bad, but because it was too flexible. Too many patterns, too many abstractions. Too many ways to write code that only its original author could fully understand. Complexity compounded with every new hire, every new feature, every new dependency. And then there was concurrency. Google's infrastructure depended on thousands of servers talking to each other simultaneously. Threads, locks, race conditions, these were daily hazards. Writing safe concurrent code in C++ required deep expertise and constant vigilance. One mistake could cascade into outages affecting millions. The irony was painful. Google had mastered distributed systems at planetary scale, yet the language used to build them was becoming a constraint. 3 engineers began quietly discussing an uncomfortable question. What if the problem wasn't the infrastructure? What if it was the language itself? Chapter 2. Designing for humans, not just machines. The 3 engineers weren't junior developers chasing trends. They were veterans. Robert Griesmer had worked on compilers and virtual machines. Rob Pike came from Bell Labs and had helped shape Unix culture. Ken Thompson was one of the creators of the Unix operating system itself. These weren't engineers trying to impress the industry. They were engineers tired of fighting their tools. Their insight was deceptively simple. Computers had become exponentially faster. Humans had not. Compilation time wasn't a hardware problem anymore. It was a language design problem. Concurrency wasn't just a threading problem. It was a model problem. Code complexity wasn't inevitable, it was encouraged. So in 2007, they started a quiet side project inside Google. No grand announcement, no marketing roadmap, just a question. What if we built a language optimized for modern multi-core machines, but constrained for human cognition? They made radical decisions. No inheritance hierarchy, no generics, at least at first, no exceptions, no macros. A tiny, rigid formatting standard enforced by the compiler itself. To many developers, this sounded absurd. Why remove features when other languages were adding them? Because every feature has a cognitive cost. Instead of complex threading primitives, they leaned into CSP-style concurrency lightweight Go routines, communicating through channels. Instead of sprawling build systems, they focused obsessively on compilation speed. Instead of expressive freedom, they enforced uniformity. The goal wasn't elegance, it was clarity under pressure. They weren't building a language for academic purity. They were building one for a codebase with billions of lines, and engineers who needed to move fast without breaking the world. The experiment had a name now. Go. Chapter 3. Simplicity as Strategy, the Backlash, and the Bet. When Go was publicly announced in 2009, the reaction wasn't applause. It was confusion. Some developers called it boring. Others called it incomplete. No generics? No traditional object-oriented inheritance? Error handling without exceptions? In a world where languages were racing to add features, Go seemed to be subtracting them. But subtraction was the point. Google didn't need a language that impressed conference audiences. It needed one that scaled teams. A language where a new engineer could read unfamiliar code and understand it quickly. A language where formatting debates disappeared because the toolchain enforced one canonical style. A language that compiled in seconds, not minutes. The most controversial choice was explicit error handling. Instead of hiding failures behind exceptions, Go forced developers to handle errors directly. Critics called it verbose. The creators called it honest. Because at Google's scale, hidden failures weren't stylistic inconveniences. They were outages. Then there were Go routines lightweight threads managed by the runtime. Instead of manually orchestrating complex thread pools, developers could spin up thousands of concurrent tasks with minimal overhead. Channels made communication explicit. Concurrency became structured instead of fragile. It wasn't magic. It was discipline, encoded into syntax. Over time, something unexpected happened. The very constraints developers resisted began to feel liberating. Code reviews got faster. Onboarding got easier. Large systems felt less chaotic. Go didn't try to be everything. It tried to remove everything unnecessary, and in a world drowning in abstraction, that felt radical. Chapter 4. From Internal Tool to Cloud Backbone. What began as a quiet internal experiment started proving itself the only way that matters, at scale, in production. Inside Google, Go was used to build real services. Not prototypes, not demos, infrastructure. Networking tools, distributed systems components that had to compile instantly, deploy reliably, and run across thousands of machines without hesitation. The results were difficult to ignore. Build times dropped dramatically. Tooling felt cohesive instead of stitched together. Cross-compilation, once a painful process, became almost trivial. A single static binary could be deployed anywhere. No dependency nightmares, no fragile runtime environments. But the real inflection point wasn't internal. It was the cloud. As containers and microservices began reshaping software architecture, Go's design aligned almost perfectly with the new world. Small services, fast startup times, minimal memory overhead, clear concurrency. Then came the projects that changed everything. Docker adopted Go. Kubernetes, originally born at Google, was written in Go. Terraform followed. Prometheus did too. Suddenly, Go wasn't just a language. It was the connective tissue of cloud infrastructure. Startups adopted it because it shipped fast. Enterprises adopted it because it scaled predictably. DevOps teams embraced it because the binaries were simple, portable, and production-friendly. The industry had shifted toward distributed systems, and Go had been built specifically for that reality. It didn't win by being flashy. It won by fitting the moment perfectly. Chapter 5. Holding the line while the world changed. Success creates a new kind of pressure. As Go adoption accelerated, the same criticisms that once seemed external grew louder from within the community. Developers wanted generics. They wanted richer abstractions. They wanted more expressive power. For years, the Go team resisted. Not because they couldn't add features, but because they understood the original constraint. Every feature increases complexity. Every abstraction shapes how millions of developers think. Under the stewardship of Rob Pike and later leaders like Russ Cox, the philosophy remained consistent: slow evolution over rapid expansion. Then, in 2022, Go 1.18 introduced generics. It wasn't a surrender, it was a measured adaptation. The design avoided the template-heavy complexity seen in C++. It focused on clarity. Type parameters were powerful but intentionally restrained. The message was subtle but important. Go would evolve, but only on its own terms. Meanwhile, the cloud ecosystem kept expanding. Kubernetes became the default orchestration layer for modern infrastructure. Observability stacks, CI/CD systems, service meshes, many of them written in Go, form the backbone of contemporary software. What started as a response to slow compile times had become a language shaping how distributed systems are built globally. Yet through all of this, Go's core identity barely changed. Simple syntax, fast compilation, explicit error handling, built-in concurrency. In a tech industry obsessed with reinvention, Go's quiet consistency became its competitive edge. It didn't chase trends. It waited for them to arrive and was already prepared. Chapter 6. Why Go was never about features. At its core, Go was never trying to compete on expressiveness. It wasn't trying to out-feature C++. It wasn't trying to out-flex Python. It wasn't trying to out-academic newer functional languages. It was solving a different problem entirely. The creators Rob Pike, Ken Thompson, and Robert Griesmer understood something fundamental about large systems. The hardest part of software at scale isn't performance. It's coordination. When thousands of engineers contribute to the same ecosystem, the biggest risk isn't that code runs slowly. It's that code becomes unreadable, fragmented, over-engineered, impossible to reason about without tribal knowledge. Go's strict formatting wasn't about aesthetics. It eliminated arguments. Its minimal feature set wasn't about limitation. It reduced cognitive branching. Its explicit error handling wasn't verbosity. It was visibility. The philosophy was quiet, but radical. Optimize for the reader. Optimize for the team. Optimize for the long term. In many languages, power accumulates through abstraction. In Go, power accumulates through restraint. And that restraint forces clarity. In a world obsessed with cleverness, Go chose discipline. In an industry that often rewards complexity, Go rewarded consistency. That's why it scaled, not just across machines, but across people. Because at Google size, and now at global cloud scale, the true bottleneck was never CPU cycles. It was human attention. Chapter 7. The real constraint. Time. There's a quiet variable running beneath this entire story. It's not syntax. It's not concurrency. It's not cloud infrastructure. It's time. Every slow build steals time. Every unreadable abstraction steals time. Every hidden bug steals time. And time, at scale, compounds. When Go's creators redesigned the compilation pipeline, they weren't chasing theoretical elegance. They were attacking latency in the developer feedback loop. Shorter compile times meant tighter iteration cycles. Tighter cycles meant faster learning. Faster learning meant better systems. That feedback loop is exponential in impact. Small gains per engineer multiply across thousands of engineers. Minutes saved per build multiply across years. Clarity today prevents outages tomorrow. Go wasn't optimized for benchmarks alone. It was optimized for momentum. That's why the language emphasizes fast builds, simple dependency management, minimal ceremony, immediate readability, because speed in software isn't just about runtime performance. It's about decision velocity. And when organizations move faster without sacrificing stability, they compound advantage over time. Today, new languages continue to emerge. Some promise more safety. Others promise more expressiveness. Some promise to replace everything. Go doesn't promise anything dramatic. It continues to do what it was designed to do. Stay simple, stay predictable, stay fast. The world that forced its creation. Distributed systems, cloud-native infrastructure, globally scaled services, has only grown larger. And in that world, clarity is leverage. The language that wasn't supposed to win didn't win by dominating headlines. It won by quietly removing friction. And sometimes, the most powerful innovation isn't adding something new. It's knowing exactly what to leave out.